Hello there, and welcome to video V5. The LLL lattice-basis reduction algorithm has been used to attack many public key crypto systems. In today's video, I'll explain how LLL can be used to break the ECDSA signature scheme in the scenario where a few bits of the per-message secrets are leaked during the signing process. This attack has been demonstrated to work in practice, including in some poor implementations of ECDSA signing in Bitcoin applications. The LLL lattice-basis reduction algorithm, along with its refinements such as BKZ, has played a central role in the cryptanalysis of many public key crypto systems. One of the earliest applications of LLL was in breaking knapsack-based public key encryption schemes. These schemes, built on the subset sum problem, were among the very first public key systems proposed in the 1970s. LLL has also been used against RSA, DSA, and ECDSA, particularly in situations where partial information about secret key material is leaked. Such leakage can arise from poor implementations, weak parameter choices, or side channel attacks. Lastly, I'll mention applications of LLL in factoring integers of the form p to the r times q, where p and q are primes, and in the number field sieve, which is the most powerful method known for factoring integers and for computing discrete logarithms. The general methodology for using LLL in cryptanalysis is the following. First, we define the lattice L so that the solution to the cryptanalytic problem is encoded in a non-zero lattice vector V that is unusually short. Second, we apply the LLL algorithm to find a short basis B for L. While LLL does not guarantee that it will find the shortest non-zero vector in the lattice, in practice, it often performs much better than the theoretical bounds suggest. This means that the target vector V might well appear among the basis vectors. Third, we check whether the vector V is indeed in B. If it is, then we can directly recover the solution to the cryptanalytic problem. I'll illustrate this methodology with a side channel attack on ECDSA. In the ECDSA signature scheme, a signer has a long-term private key A. To produce a signature on a message, the signer generates a per-message secret key K and then uses both K and the long-term private key A to form the signature. Both A and K must be chosen uniformly at random from the integers between 1 and n-1. Just as importantly, the fresh per-message secret key K must be generated for each new message that is signed. In practice, though, information about some per-message secrets K might leak during the signing process through side channel attacks. These attacks can exploit weaknesses such as poor implementation, weak random number generation, timing information, electromagnetic radiation, and so on. The information obtained via these leaks can sometimes be used to recover the long-term private key A. Once A is compromised, the entire ECDSA implementation is completely broken. I'll give you a quick overview of ECDSA domain parameters, key generation, and signature generation. Don't worry if you aren't already familiar with ECDSA. You'll still be able to follow along with the attack, because the attack relies only on the so-called ECDSA signing equation. Let's begin with the ECDSA domain parameters. These are publicly known and shared by all users of the system. They consist of an elliptic curve E defined over the integers modulo a prime p. The prime n, which is the number of points on the curve, a generator point p on the elliptic curve, and a collision-resistant hash function such as SHA-256. To generate a key pair, a user Alice does the following. Alice randomly selects an integer a between 1 and n-1 and computes the elliptic curve point A equals A times P. Alice's public key is the point A, whereas her long-term private key is the integer a. Recovering the private key from the public key is an instance of the elliptic curve discrete logarithm problem, which is believed to be very difficult. To sign a message M, Alice does the following. She first computes the hash m of the message. She then chooses a fresh secret k uniformly at random between 1 and n-1. Using k, she computes the elliptic curve point r equals k times p. She extracts the x-coordinate of the point r, reduces it modulo n, and calls the result r. Note that r is a non-zero integer between 1 and n-1. Finally, Alice computes another integer s, defined as the product of the inverse of k times m plus ar, all modulo n. Alice's signature on M is a pair of integers r and s. To understand the side channel attack on ECDSA, it will suffice to remember the signing equation, which is this equation for signature component s. Since the side channel attack is on the ECDSA signature generation process itself, we won't need to look at signature verification.
We'll first consider the situation where an attacker manages to learn partial information about the per-message secrets used in two ECDSA signatures. Concretely, they discover that the first half of the bits of each per-message secret k are 0. This scenario is rather contrived, but it nicely demonstrates how lattice techniques can play a role in side-channel attacks.
Recall that an ECDSA signature on a message M is comprised of a pair of integers r and s, each between 1 and n-1. The signature component s is defined to be k inverse times m plus ar modulo n, where k is a per-message secret, a is the long-term private key, and m is the message hash. Knowledge of a signed message MRS yields a linear congruence equation in two unknowns, a and k. The attacker knows M, R, S, and N, but not A or K. Now suppose that the adversary obtains two signed messages, M1R1S1 and M2R2S2. From the two signature equations, the adversary can derive two linear congruences. Eliminating A from the two congruences gives a single linear congruence relating the two per-message secrets K1 and K2. And rearranging yields this linear congruence modulo n. Note that the only quantities that are not known to the adversary are K1 and K2, which are non-zero integers modulo n.
Now, one linear congruence in two unknowns does not usually suffice to recover K1 and K2. However, it might be possible to solve for K1 and K2 if the attacker already has substantial partial information about K1 and K2, for example, an upper bound on their size.
If the adversary can solve for K1 and K2, they immediately recover the long-term private key A, and thus the ECDSA instance is completely broken. We'll assume now that K1 and K2 are upper bounded by some number capital K, which is quite a bit smaller than n and known to the attacker. We'll specify K later. By combining terms, the linear congruence can be written as K1 plus T times K2 plus U congruent to 0 modulo n, where T and U are these quantities, which can be computed by the adversary. You can check this for yourself. This congruence can be written as an equation K1 plus T times K2 plus n times x plus u equals 0, where x is an integer. The adversary knows T, n, and u, but does not know K1, K2, and x. We're now ready to define the lattice that will let us find K1 and K2. Consider the three-dimensional integer lattice L with basis vectors n00, t10, and u0k. The basis matrix for L is this 3 by 3 matrix B. The volume of the lattice is the absolute value of the determinant of B, which is n times k. Now, you can check that B times the integer vector xk21 is this lattice vector V, which simplifies to minus k1, k2, k. The first two components are the unknown per message secrets k1 and k2, and the third component is the known quantity capital K. The length of V is the square root of the sum of the squares of its coordinates, which is at most the square root of 3 times k, since k1 and k2 are at most capital K. Now, the Gaussian heuristic predicts that the length of a shortest vector in the lattice is approximately the cube root of its volume, which is the cube root of n times k. Thus, if the length of V is much smaller than the cube root of n times k, one can expect V to be a shortest non-zero vector in the lattice, and hence recoverable by an algorithm that solves SVP. This condition can be approximately written as k less than the square root of n. This requirement is satisfied if more than half of the leftmost bits of each per message secret are known to be 0. So if k1 and k2 are both much smaller than the square root of n, then the target vector V is likely to be a shortest non-zero vector in the lattice, and therefore can likely be determined by solving SVP in L. Applying LLL to compute a short basis for L will often produce V or its negative among the basis vectors. From such a vector, the adversary reads off k1 and k2 and then immediately computes the long-term private key A from the signing equation. Thus, the ECDSA implementation is completely compromised.
Let's now turn to a more realistic scenario, in which only a few bits of each per message secret are leaked. For concreteness, we'll consider the case where those leaked bits are least significant bits. However, the attack can be adapted just as easily if the leaked information were most significant bits, or even some middle portion.
Okay, suppose the adversary has obtained n signed messages MIRISI. Suppose also that the adversary has obtained a few least significant bits of each per message secret KI used to sign MI. More precisely, let T be the bit length of the ECDSA parameter n, so that every KI is at most T bits long. Let beta I be the L least significant bits of the binary representation of KI, and let alpha I be the remaining T minus L bits. Then KI equals alpha I times 2 to the L plus beta I. We're assuming that the adversary knows the beta I's but not the alpha I's. Defining K to be n divided by 2 to the L, we see that each alpha I is less than K. Next, for each I, eliminate A from the signing equations for the ith message MI and the last message MN to obtain a linear congruence where the only unknowns are KI and KN. Replacing each KI with alpha I times 2 to the L plus beta I yields this congruence. Finally, multiply both sides by the inverse of 2 to the L modulo n, simplify, and eliminate the mod n to obtain equations alpha I plus Ti times alpha n plus Ui plus xi times n equals 0 for each I between 1 and n minus 1. So we now have n minus 1 such equations, where the unknown quantities are the alpha I and the xi. Consider the n plus 1 dimensional integer lattice L with basis matrix B. The basis vectors are the columns of the matrix. Notice that B is an upper triangular matrix, so its determinant, which is also the volume of the lattice, can be seen to be n to the power n minus 1 times k. Now, we have a lattice vector V, defined to be the matrix B times the vector x1, x2, up to xn minus 1, alpha n 1, which you can check equals minus alpha 1 minus alpha 2 minus alpha n minus 1, alpha n k. Notice that the first n components of V are the unknown alpha I values that the adversary is trying to recover, and the final component is k, which the adversary knows. This lattice vector has length bounded by the square root of n times k. The Gaussian heuristic predicts that the shortest non-zero vector in this lattice should have length approximately given by this expression. Plugging in the expression for the lattice volume gives this approximation, which after simplification gives this expression. Now, we desire that the target vector v has length that is much smaller than the above estimate for the first successive minimum. Thus, we require this inequality to be satisfied, which simplifies to this inequality. Recall that t is the bit length of n, so the bit length of k is approximately t minus l. Eliminating k and n, we see that the desired inequality simplifies to n times t minus l much less than nt minus t, which yields n much greater than t over l. Thus, if n is much greater than t over l, then the target vector is likely to be a shortest non-zero vector in the lattice. Therefore, v can likely be determined by solving SVP in the lattice. This can be accomplished by using LLL to find a short basis for the lattice. One can hope that one of the basis vectors is v, or its negative, i.e. a vector with k as its last component. If such a vector is indeed in the basis, then the adversary has learned the ki. They can then immediately compute the long-term private key A from the signing equation.
Here is a summary of the ECDSA attack. Suppose that the adversary obtains the L least significant bits of each per message secret, ki, for n signatures. Here, n is significantly greater than t divided by L, where t is the bit length of the ECDSA parameter n. Then the adversary can likely determine the per message secrets, ki, by using the LLL algorithm to find a short basis for a certain lattice. Once the adversary has determined a per message secret, they can immediately compute the long-term private key.
Even though the analysis of the attack is heuristic, experiments have shown that the attack is successful even when as few as 2 bits of each ki are leaked. The attack can be adapted to situations where the adversary obtains only a few most significant bits of per message secrets, or a few middle bits of per message secrets. Lastly, I'll mention that the attack has been shown to be effective in breaking poor implementations of ECDSA in practice, including in Bitcoin, where ECDSA is used to sign transactions. Here is a toy example of the ECDSA attack. Take the ECDSA parameter n to be this 21-bit prime number. Let the number of signed messages be n equals 6, and fix the bound k equals 30,000. We'll suppose that each per message secret ki is less than k. This is roughly equivalent to knowing that the 6 most significant bits of each ki are 0. The 5 congruences that the adversary can derive from the 6 signed messages are ki plus ti times k6 plus ui congruent to 0 modulo n for I between 1 and 5. Let's suppose that the per message secrets are these numbers. The adversary's task is to find them. I'll generate a concrete instance of the linear congruences for the adversary by selecting random ti between 1 and n minus 1, and then setting ui to equal minus ki minus ti times k6 modulo n. Here are the resulting ui values. So, the adversary's task is to determine the ki given the ti, ui, and n. The associated 7-dimensional integer lattice L is defined by this 7 by 7 basis matrix. Running the LLL algorithm on that basis produces the following lattice basis. A quick inspection of the output reveals that the negative of the first 5 per message secrets appear as the first 5 coordinates of the first basis vector. The adversary can use any one of these per message secrets to compute the long-term private key A. Correctness is confirmed by checking that the public key capital A equals little a times P. Here are some references that explore other applications of the LLL algorithm in cryptography. First, the 2001 survey by Fong Nguyen and Jacques Stern. Next, the 2024 paper by Gabriel de Micheli and Nadia Henninger, which provides a broad overview of lattice-based attacks on RSA and elliptic curve systems. My presentation of the ECDSA side-channel attack draws directly from this paper. Finally, the 2019 paper by Jochen Breitner and Nadia Henninger, which examines weak implementations of ECDSA signing in cryptocurrencies, including Bitcoin.
In our course, we've only described the basic version of the LLL algorithm. We omitted many optimizations, such as the use of floating point arithmetic. In the next video, we'll mention these optimizations and also outline BKZ, a block variant of LLL. BKZ is considered the fastest algorithm for finding short bases of a lattice. I look forward to seeing you in V6.